Welcome to Chapter 3. In this chapter, we're going to be looking at the concept of the determinant. We're covering 3 sections here, and as you can see, we're kind of grouping all 3 of them together and looking at their topics all at once here. So we are going to be talking about what is a determinant, the definition. We're going to be looking at different properties of determinants, and then a technique for finding determinants called cofactor expansions. So to start off, we need to kind of establish some stuff right off the bat here. So we assume that A is a square matrix that's going to be necessary in order to compute a determinant of a matrix. We're going to be associating this n by n matrix with a number, which is written either det of A or looks like absolute value of A or magnitude of A, something like that. But that symbol represents a determinant being taken. Interesting thing about determinants, we can use them to also identify invertibility in matrices. So this is something that we'll be talking about a little bit more towards the end of the lesson. But an n by n matrix is invertible if and only if the determinant of that matrix is non-zero. And again, we'll be going more in detail on that a little bit later. So what is the determinant of A? How do we find this numerical value that we're associating with a matrix? Well, the way we find the determinant purely depends on the size of the matrix that we're working with. If we have a 1 by 1 matrix, so there's this little single element matrix, the determinant of the matrix is just whatever that number is. So determinant of A is just A. So that's the most straightforward case. If we have a 2 by 2 matrix, so we're trying to find the determinant of this 2 by 2, that one we calculate using AD minus BC. So that's AD minus BC. So basically we just multiply across and then subtract. So the 2 by 2, also pretty straightforward and formulaic. The 3 by 3 gets a little more interesting. So the determinant of this 3 by 3 matrix, we do have a formula for it, but this is not necessarily the best or simplest way to calculate it. A lot of times we have better methodologies that help us solve problems like this. The first method that we have is a method that would be similar to the cross product. That you see in multivariate calculus. So typically when you learn how to compute a cross product, it's using a 3 by 3 matrix of, vector components. So you take the vectors and then you put them all into this form. But the way that we handle that is we take the determinants. So we've got A, B, C, D, E, F, G, H, I. You take the first component, the 1, 1 component, you block off its row and its column, and you multiply by the determinant of this submatrix, this 2 by 2 matrix within the 3 by 3. So we get A times the determinant of E, F, H, I. And then minus, we go to the second component, so the B. And then we block off its row and column, give us D, F, G, I for the remaining 2 by 2. And then plus C, so third component, block off row and column, we're left with D, E, G, H. And now if we compute these 2 by 2s, we end up getting, right, EI minus FH. So A times EI minus FH minus B times DI minus FG plus C times DH minus EG. And of course, that formula matches this one right here. So that is equivalent. Okay, and this is a method that we should hopefully be familiar with from our experiences in Calculus 3. Now, there is another method that we have to be able to evaluate a 3 by 3 determinant, and this is called the arrow method. So what we're going to do is we're going to set up our determinant. Okay, then the next thing that we do is I'm going to replicate these first 2 columns off to the right-hand side of the determinant. So we got ADG again and BEH again. Now, the way that this works is we're going to be drawing some arrows. Those arrows are going to indicate the products that we need to take in order to compute this determinant. So we start with this upper left-hand corner, and we're going to go down those 3 right there. Then we go over 1 and we do these 3. Then we go over 1 and we do these 3. And each of these get a little plus under them. Now we go, on the flip side, we go to the bottom left corner and we go up that diagonal there. Next one, we go up that diagonal, and the next one, we go up that diagonal. And each of these get a minus on them. Basically, what we need to do with these is we're going to multiply down these arrows and up these arrows, but we're going to give them the appropriate sign depending on what direction the arrow is pointed. So for these ones down here, we get AEI, and it's positive, and then plus BFG plus CDH. And now these ones up here are going to get negatives, so it's going to be minus CEG minus AFH minus BDI. And now all we need to do is a little rearranging. So we know that our formula has A, B, and C out here in the front. So we'll take the A terms together, we'll take the B terms together, and we'll take the C terms together and factor out the common term. So when we factor out A, we're left with EI minus FH. For B, we have FG minus DI. So if we want to be consistent, there's a negative out here. So we could factor a negative out of both of those. So we'll take minus B. That'll become plus DI minus FG. Just if we want to be consistent with this version of the formula. But if you're just computing these as numbers, it doesn't really matter. Plus C times DH minus EG. And once again, that is that formula. So the arrow method allows us to calculate the determinant of a 3 by 3 matrix. And this method, it's up to you to decide whether you like this method, if this method feels more efficient for you, or it's easier to remember or understand, then by all means, feel free to use the arrow method. If you don't like the arrow method, if you just like sticking with your kind of previously known work with the cross product, it's all the same. Like the results are all the same. So no matter how we handle that, you'll get the same thing. Now, once we move past 3x3s, the methods are not quite as clear-cut. So, right, a 1x1, the determinant is just the term. 2x2, we have AD minus BC. 3x3, we have these two alternative methods. All of these methods do not work for 4x4s and larger. We have to come up with another way to determine a determinant for larger matrices. So if we look at the next page here, we have a bit of terminology that we need to introduce here, and these terms are going to help us in finding these determinants. First, we need to talk about the minor of the element A sub ij, which is denoted M sub ij. The minor of that element is the determinant of the n-1 by n-1 submatrix obtained by deleting the ith row and jth column. So this process does mimic very similarly that cross product idea. In fact, we're going to find as we go through this process that the cross product methodology is just a special case of this property that we're talking about. So, for example, if we have this 4x4 matrix and we want to determine the minor of the 3-4 component, then we need to compute the determinant of the submatrix obtained by deleting its row and its column. So we delete its row and its column. That, of course, leaves us with 1, 2, 3 by 1, 2, 3. So we have a 3x3 submatrix to compute now. So let's go ahead and just get that. So that's 1, 2, 3. Negative 1, 1, 5, 2, negative 2, 1. We could go ahead and use the arrow method. So go 1 times 1 times 1 is 1, plus 2 times 5, and then if continuing on, that would give us that 2. 2 times 5 times 2 is 20. Plus 3 times negative 1 times negative 2, that's 6. Minus 2 times 1 times 3 is 6. Minus negative 2 times 5 times, it continues up here if we put that over here. So that's negative 10. So minus negative 10 is plus 10. And then 1 times negative 1 times 2. So that's negative 2. So that's minus negative 2 or plus 2. So we get, that's 21. These cancel, 31, 33. So the minor of this element, of the 3-4 element in this matrix, is 33. Next up, we need to talk about the cofactor of the element A sub ij, which is denoted C sub ij. Now the cofactor, this is computed by taking the minor times -1 raised to the I plus j power. So essentially, we're taking the same calculation as the minor, okay? So the cofactor is the minor, but it's plus or minus depending on the row and the column that the minor is in. So like in the previous example, so the cofactor for the 3, 4 element is going to be -1 to the 3 plus 4 times the minor, which we got is 33. So this gives us -1 to the 7th times 33. -1 to the odd power, that stays -1. So the cofactor is -33. Now, what this tells us is the relationship between the row number and the column number actually can tell us whether or not this sign is going to change. So if we were looking at, like, for example, a 3 by 3 matrix, if we were in the 1, 1 position, that's -1 to the 1 plus 1. So that is -1 squared, which is +1. If we move over to the 1, 2 position, that becomes -1 to the 1 plus 2. That's -1 cubed, which is an odd power, so it stays negative. And this pattern will continue. So you'll see anytime that the row and column number add up to an even value, this becomes +1. Anytime they add up to an odd value, it stays -1. And so this pattern essentially alternates throughout the entire matrix. So the position in the matrix tells you whether or not it's going to change sign or keep the same sign. And this isn't just for 3 by 3s, like it would continue on for 4 by 4s. It kind of makes this checkerboard pattern. So, and if you recall from the cross product method that we looked at for the 3 by 3, we had this formula that had A with a -b and a plus C. Back in Calc 3, we basically tell you these alternate plus, minus, plus. We never really explain why that's the case, but it's actually because of the cofactors. Because here we're in the 1, 1 component, and here's the 1, 3 component. Those cofactors result in positives, whereas this one is in the 1, 2 component. It results in a negative. That's why you get the minus in front of the second term on your cross products. So when it comes to computing a determinant using cofactors, we have what is called the cofactor expansion theorem. The cofactor expansion theorem says for an n by n square matrix, the determinant of A is equal to AI1 CI1 plus AI2 CI2 plus AI3 CI3, etc., all for the expansion of one of the rows of the matrix. Or that's also equal to A1J C1J plus A2J C2J, etc., corresponding to the expansion of one of the columns of the matrix. So, in other words, if we want to find the determinant of a matrix of any size, this method will work for matrices of any size. We just need to expand either one of the rows or one of the columns, take the component times its corresponding cofactor, plus the next component in the row or column times its corresponding cofactor, etc., etc., etc. So this process can get fairly long if you have larger and larger matrices, but this is the method that we have. So there's not really any good, shortcuts or tricks for these higher dimensional matrices. So just as a note here, so it doesn't matter what row or column you choose. So we can choose any row or column. So it doesn't matter, but there are smart ways of choosing particular rows or columns to do the cofactor expansion on. Namely, if you're trying to minimize your work on a row or a column like this, the more terms that you can get eliminated from this equation, the better. And so the key to picking better rows or columns is looking for any zeros. So zeros are the key. Because if I have a row that's mostly zeros, then it doesn't matter what the cofactor is, because the A term is 0, and this term is 0, and so this term is 0, and you don't need to compute a lot of these cofactors if the term next to them is 0. So anytime you can find a row or a column with zeros in it, that's going to be a very helpful way to solve for a determinant. So let's look at this example down here. So for this 4 by 4, we're going to find the determinant using cofactor expansion. We can choose any row or column that we want, and you will get the same answer for all of them. But there is one that is noticeably better than the others, and that's, of course, going to be this second column. Of course, because it has a lot of 0 terms in it, it'll give you the exact same answer as if you were to, say, expand, the fourth column or the third row or one of those with no zeros. But this one's going to minimize our work. So we're going to expand the second column. So determinant of A. So if we're in second column, that's A12, C12, plus A22, C22, plus A32, C32, plus A42, C42. So theoretically, we would have to compute 4 different cofactors to do this, but A12 is 0, A22 is 0, and A42 is 0. So all we really have to do is compute A32 times C32. So we do have to get one cofactor. So we're going to get, C32. So that's -1 to the 3 plus 2 times the determinant of that submatrix. So block off the row and column and put the remaining 3 by 3 in this matrix. So that's going to be, 2, 8, 1, -1, 3, 5, 3, 1, -4. The -1 is raised to an odd power, so that's going to be a negative here. And the determinant of this 3 by 3, if you go through that process, gives us 44. So we get the cofactor of the 3, 2 component is -44. So we get A32 is 2. So 2 times -44. So we get -88. And that would be the determinant of this matrix A. And again, you would get the same value for any row or column that you chose to expand. Now, let's take a look at a bigger example. So this example right here, we have a new matrix that is 5 by 5. So to compute the determinant of this one, we need to expand any row or column. There's a couple good choices for this one. Notice there's a lot of zeros down here. So you can choose any row or column will work. I'm going to go ahead and go with the first column here. You could also pick the last row. Both of them have the same number of zeros in them. But I think we'll go ahead. So I'll expand first column. Again, you didn't have to choose the first column specifically. All right, so the determinant of A, that's going to be A11, C11. And then every other term in that expansion is going to become 0. So it's really just this. So A11, C11, that's going to be, so A11, C11 is going to be -1 to the 1 plus 1. So that's going to be +1 times the minor at the 1, 1 position. That minor is going to be the determinant of the submatrix when you block off row and column. So this 4 by 4 here. So this is the determinant of the 4 by 4 matrix. So let's see, the A11 component, that was 3. Now, in order to get the determinant of the 4 by 4 matrix, we have to do a cofactor expansion on it. We can again choose any row or column. I'm going to stick with my first column here. So that would be, again, the A11, C11 component. So we'll expand first column of the 4 by 4. So let's see, the 3's still out there. We get the 1, 1 component here, that's -2. That's going to have a value of +1, right? Because to the 1 plus 1 for the cofactor. And then times the minor of the 1, 1 component within that 4 by 4. So what does that mean? Well, this minor is going to be the determinant of the submatrix blocking off row and column of the 4 by 4. That's going to give us this 3 by 3. So this one is asking us to get determinant of the 3 by 3 matrix. Then when it comes to computing the determinant of that 3 by 3 matrix, we have the tools to be able to compute that. Although if you wanted to continue this pattern, if you think about how you compute a cross product, right, you take the components from this one and you block off their row and column one by one and compute the subdeterminant. That is essentially just a cofactor expansion. So you wouldn't necessarily have to choose the first row. You could pick like the first column here if you wanted to try it and do it a little bit easier. But we also have like the arrow method. You can just take it, using those standard procedures. But that one, so we get, this is 3 times -2 times, if you were to compute the determinant of this 3 by 3, you would see that it gives you 15. And thank you for bearing with my color coding here. Just want to be as clear as possible. So we get 3 times -2 times 15, which works out to -90. So that would be the value of that determinant. This is the determinant of that 5 by 5. Using a cofactor expansion on the first column of the 5 by 5, then using another cofactor expansion to get the determinant of the 4 by 4, and then computing the 3 by 3 either via another cofactor expansion or the arrow method, or that typical cross product method, which again is just another example of a cofactor expansion. Now, the interesting thing about cases like this, so this really large matrix, ultimately when we whittled it down and got all of these values here, it became just kind of a product. Down here at the bottom, we just multiply everything together, and that gave us the -90. It turns out when you have special matrices that you're working with, notably because we're dealing with square matrices, if the matrix is upper or lower triangular, we can compute the determinant much more simply by taking A11 times A22 times A33, etc., all the way down to ANN. So it turns out, if you have an upper or lower triangular matrix, you can compute the determinant of that matrix simply by multiplying the components of the main diagonal. Okay, so you can multiply the components of the main diagonal to get the determinant. So in this previous example, notice this is upper triangular, right? Everything below the main diagonal is 0. So if we just take all the terms on the main diagonal and just multiply them together, 3 times -2 times 5 times 3 times 1, that's -6 times 5 is -30 times 3 is -90. Found using a lot less work and still yielding the same answer. Properties like this can be very helpful, for obvious reasons, in computing determinants more quickly. But we can use properties like this in conjunction with what we know about matrices to help us compute determinants in another way. So if we look at the top of the next page, the elementary row operations actually do have an effect on the determinant of a matrix. So if you had a matrix that had a determinant and you performed an ERO, an elementary row operation, on that matrix, it could impact what the determinant of the new matrix is. So here we have our 3 EROs. If you go from matrix A to B using a permutation, okay, by permuting 2 rows, the determinant of the new matrix B is the opposite of the determinant of the original matrix A. Okay, so permuting 2 rows negates the determinant. If you use the multiplication ERO to get from A to B, the determinant of B is now K times the original determinant of A. Right? So again, if you multiply a row by K, it multiplies the determinant by K. The addition operation, where you're adding a multiple of one row to another row, actually that one has no impact on the determinant. So we can perform that ERO all day, and it's not going to change the value of the determinant of a matrix. Now, what this means for our determinants is we can, instead of computing the determinant of maybe a more messy matrix now. Now, obviously, the example we're going to do is a 3 by 3. That's not that bad. But if we were to get, a 5 by 5, a 6 by 6, something larger like that, and we don't want to do multiple cofactor expansions to it and go through that whole process, what we could do is we could try to put this matrix into a form like an upper triangular form, take the determinant of the easy matrix at the end, and then backtrack the changes that we made to find the determinant of the original. Okay, so let me say that one more time. So we're going to turn the matrix into an easier matrix, like an upper triangular. In doing so, we can compute the determinant of the easy matrix at the end, and then backtrack the changes we made to find the determinant of the harder matrix from the beginning. All right, so let's take a look at this example here. So we're going to start with the matrix A. So that's 2, 1, 3, negative 1, 2, 6, 4, 1, 12. I want this component to be a pivot, so I'm going to permute 1 and 2. So negative 1, 2, 6, 2, 1, 3, 4, 1, 12. And then I'm going to use this to clear out everything below it. So I'm going to add 1 to 2 times 2, and add 1 to 3 times 4. So we get 0, 5, and 15, 0, 9, and 36. I'll go ahead and multiply the second row by 1/5. So negative 1, 2, 6, 0, 1, 3, 0, 9, 36. And then I'll add second to third times negative 9. And that would be 9. And this would be our matrix B. Now, it's not perfectly in row echelon form, right? This isn't a positive 1, that isn't a 1 at all. But we didn't need row echelon form. What we wanted was upper triangular, which this is. This is an upper triangular square matrix. So what we can do with this now is we can calculate determinant of B and work backwards. So this determinant, we multiply all the terms on the main diagonal. So that's negative 1 times 1 times 9. So determinant of B is negative 9. Now let's go ahead and look back at what we did to get from A to B. So we permuted 2 rows, which means that the determinant got multiplied by negative 1. So let me just write it in symbolically. So times negative 1. Here, from this matrix to this one, we did 2 addition EROs, which results in no change. Here we did a multiplication ERO, so that's going to get multiplied by 1/5. Here we did an addition ERO, so again, no change. So now if we backtrack and undo the changes that were made to get back to determinant of A. So from here to here, there was no change. From here to here, so we're still at negative 9 right now. Going this way, we had multiplied by 1/5. So this is 1/5 of what this one was. So we need to undo the effect. So that just means we're going to multiply by 5. So that's going to be negative 45. No change was made here. So still negative 45. And then it was multiplied by negative 1. So we need to undo that effect. So we get determinant of A is positive 45. And of course, we found this method without having to use the technique of cofactor expansion. On a 3x3 like this, this is not necessarily the fastest way to do it, but this is, again, just a proof of concept. You could use this for any size matrix, use the EROs to simplify it, get it to a place where you can take the determinant very easily, and then just undo the effects on the determinant that you made along the way to get back to the original. All right. Now, a couple more things to talk about here. Recall back at the beginning of the section, I was introducing the idea of what the determinant tells us about invertibility. If you recall the invertible matrix theorem from chapter 2, we're going to add on one item to this theorem today, and that is its item G is the next continuation here. It is that the determinant of A is not equal to 0. So we can say A is invertible if and only if the determinant of A is not 0. So we can use the determinant to actually tell relatively quickly whether or not a matrix is invertible. This is a very handy test for us because obviously we saw back in chapter 2 that you can determine invertibility and find the inverse using EROs. But if we can do just a quick test with a determinant, that makes it a lot faster. Now, we are going to talk more about invertibility involving determinants. But first, just a list of some different determinant properties here that we might need to know that'll be helpful to us. Determinant of a constant times a matrix is k to the n times determinant of A for any real number k. Determinant of a transpose is equal to determinant of A. Determinant of A inverse is 1 over determinant of A. If A has a row or column of all zeros, then its determinant is 0. And hopefully that makes sense. If you're going to do a cofactor expansion on a matrix, you want to pick the row or column with the most zeros. If there's a row or column with all zeros, then you won't have to compute any cofactors. You'll just take 0 plus 0 plus 0 all the way down. The determinant of A times B is the determinant of A times the determinant of B. There is, however, no formula for a determinant of A plus B. We cannot take it to be determinant of A plus determinant of B. It doesn't work that way. You can find many counterexamples to show that that's in fact the case. So if we know these properties and we know some information about matrices, we can compute complicated determinants of much more like rigorous expressions using these properties. So there's a couple examples here. Suppose that A is a 4x4 matrix and that its determinant is 5. What is the determinant of 2A? So determinant of 2A, that would be its k to the n, so the scalar raised to the power of the dimension of the matrix. This is a 4x4, so that's 2 to the 4 times determinant of A. And determinant of A is 5, so that's going to be 2 to the 4th times 5, which gives us 80. Now, what about something a little more complicated? If we know the determinant of A, B, and C, find the determinant of this expression, this big matrix that's created by inverting, multiplying, transposing, and doing all that kind of stuff. So the determinant of BC inverse times A transpose B squared. Let's go ahead and expand all of this out as much as we can. BC inverse, if you remember properties of matrix inverses, the inverse of a product is basically the reverse product of the inverses. So C inverse B inverse, A transpose, and then B squared, I'm going to go ahead and list it out as B times B. Now we know that the determinant of the product is the product of the determinants. So we can go ahead and split this into individual determinants. Times determinant A transpose times determinant of B times determinant of B. The determinant of the inverse is just 1 over, so that's 1 over determinant of C. Same thing here, 1 over determinant of B. The determinant of the transpose is the same as the original, so that's just determinant of A. And then determinant of B times determinant of B, that's determinant of B squared. So the squared does carry through. And now these are all things that we know from the problem, right? Determinant of A is 3, determinant of B is 5, determinant of C is 2. So that's going to be 1 over 2 times 1 over 5 times 3 times 5 squared. Multiply all of that out, and we get 15 over 2, or 15 halves. So we can compute the determinant of a much larger matrix or a more complicated matrix simply by knowing the determinants of the pieces that went into the calculation like this. Now, we can use determinants like we saw back up here with the invertible matrix theorem. We can use determinants to test whether a matrix is invertible or not. it turns out we can also use determinants to find the inverse of a matrix. And this is done using what we call the adjoint method for A inverse. So a little bit of terminology here. If every element of A is replaced, so every element is replaced by the corresponding cofactor of that element, we get what is called the matrix of cofactors, denoted M sub C. So if you take every element of a matrix and replace it with its own cofactor, right? So you compute the subdeterminant, block off its row and column, you compute the minor, right, the determinant of the remaining terms, and then multiply either by +1 or -1, depending on its position. So create the matrix of cofactors. If you took the matrix of cofactors and transposed it, so matrix of cofactors transposed, this is called the adjoint of A, which is denoted ADJ of A. The adjoint theorem tells us that A inverse, so the inverse of the original matrix, is equal to 1 over the determinant of A times the adjoint of A. The adjoint theorem says that the inverse of the matrix can be computed by taking 1 over the determinant of A times the adjoint of A. And actually, if you think back to chapter 2 when we were finding the inverse of a 2x2 matrix, remember the formula for that was 1 over AD minus BC, and then you interchange the terms within the matrix. This AD minus BC here, that is the determinant of a 2x2. We just saw that today. So this formula is actually derived using the adjoint method. We just, of course, don't say that right away, but here we are now. We can use the adjoint method just as well as we can use the EROs that we saw back in chapter 2. So, for example, use the adjoint method to find the inverse of this matrix A. So the determinant of A, which just for the sake of time, I'm just going to tell you a lot of this stuff. So the determinant of this matrix is 26. You can compute that. The matrix of cofactors for this matrix. So like, for example, like for the 1, 1 component, we block off its row and its column. We compute the 2x2, so that's 2 minus -5, so that's 7. And it's in the 1, 1 position, which means that it's, right, it's plus, minus, plus, like that. So it's going to be just positive 7. If we went on to the 1, 2 component, block off its row and its column, we get 4 minus 0, so that's 4. But it's in the 1, 2, so that's -4. And then we do it for the 1, 3 component, block off row and column. So that's -2 minus 0. And it keeps its same sign because of its position. And then et cetera, et cetera. So if we go from here, we get this one, block off. That's -6 minus 0. But then its position makes this a 6. And I'll go ahead and just fill in the rest of these myself. So that's going to be a 4. That one's going to be a 2. That's a -15. That's a -10. And that one's an 8. So that's going to be our matrix of cofactors. So our adjoint, which is the transpose of the matrix of cofactors. So we transpose this matrix, interchange row and column. So that's 7, 6, negative 15. That's negative 4, 4, negative 10, negative 2, 2, and 8. So the inverse of this matrix is 1 over 26 times 7, 6, negative 15, negative 4, 4, negative 10, negative 2, 2, and 8. And that would be it. You could alternatively, if you wanted to not have the coefficient out in front, I mean, you could go through the process of, 7 over 26, 3 over 13, negative 15 over 26, negative 2 over 13, simplifying a bit, 2 over 13, negative 5 over 13, negative 1 over 13, 1 over 13, and 4 over 13. Like that. So either way, it is equivalent. So you would get the same result. But this now provides us with a new tool to be able to compute the inverse of a matrix, not only using EROs like we saw back in chapter 2, but by using determinants and by using the adjoint. So by taking the matrix of cofactors and then transposing it. But that brings us to the end of chapter 3 and the end of our discussion on determinants.